Welcome to lecture number 8, and in this lecture I would like to talk about some of the more theoretical aspects of computer science, basically about computability theory and maybe a bit about complexity theory. But I just want to say that I was talking about mathematical functions in one of the lectures before, and I said mathematical function always returns. I don't know if I didn't actually said this, but in case I said that a mathematical function that also returns a value, then we have to clarify this is about computable functions. But it can also be the question whether a function is computable at all. So imagine a function that for some inputs ends up in an endless loop. So this is not an algorithm, because we said the algorithm always terminates, and it is not a computable function or a decidable function, because a computable function is a decidable function. This is another term which is used in this context. Computability theory is about determining what makes a function computable. So if you have a simple mathematical function like f of x is 3 times x plus 2, well, this is computable, because no matter what value we choose for x, we get a result. In the scope, of course, of the values supported. So the x has to be a decimal value, for example, or an integer, but not a string. What is if we have, for example, a function that returns true if another program terminates, and that returns false if another program does not terminate? How should a program check whether another program terminates? So usually you do this by simply making the program call the other program and then check. Well, if it terminates, then obviously it does terminate. But if it does not, we don't know. We can say it didn't terminate until a certain number of instructions were processed. Okay, but we have no idea whether it will eventually terminate or it will never terminate. So such a program is actually undecidable. It is not computable. And I'm talking about programs and functions, so maybe this is a bit confusing, but let's say we can use these terms more or less equivalently. And this problem is also called the halting problem. Halting problem is about the question whether we can create such a program that checks whether another program holds. And there has been results on this that this is not possible. We can only write a program that says yes, the other program holds if it does hold, but we cannot determine for sure that the other program definitely will not hold, or if it eventually will hold, if we wait for years and we still haven't got a result. And it is quite interesting, actually. A computable function can be many things. It can even be a function that takes a value, and depending on the value it returns another value. And if this is a complete enumeration, of all possibilities, of all accepted parameters, then this is also a computable function. So it does not have to be a mathematical function in the strict sense, like the example I cited at the beginning with f of x being 3 times x plus 2. So this is also something that is quite, let's say, entertaining. It can be a nice hobby to work on functions and determine whether they are computable or not. What I also wanted to say in this lecture is that there are some formalisms which are used in theoretical computer science instead of the regular notation as used in computer programs. Of course, one is pseudocode, so you write programs that are not executable, that cannot be compiled, but that have a syntax similar to a programming language. But what I actually was wanting to talk about is something slightly different, namely automata and finite state machines. So imagine you have a sequence of zeros and ones, which is the input. And you have an automaton that gets this input. And it starts at some position, similar as the central processing unit of the computer does. And then the term, it checks the value, and depending whether it is 0 or 1, the automaton outputs a certain value, and then it decides into which state it switches. And so the state of the automaton decides together with the input value what the output value is. So this is a formalism that can be used to evaluate certain inputs actually, and also to represent certain types of algorithms. And one of these formalisms is a Turing machine. And this Turing machine is very powerful because any algorithm that can be computed by a regular computer can be represented by a Turing machine. The Turing machine is a bit different from other automata because it can overwrite the input, and it can go both to the right or to the left. If we assume that the input is some sort of tape where you can walk left or right. We just have to make sure that there is at least one state which is called an accepting state, and maybe also a state which is called a rejecting state, but at least we must have an accepting state. So when this accepting state is reached, then the program terminates. So this is mostly used in the theory of formal languages because the input we feed such a Turing machine with can be a word, so to say, in a formal language. And well, we can check with a Turing machine whether this word is accepted or not. So there are several classes of formal languages, and depending on the class of the formal language, there are various types of automata that can be constructed that would be able to accept such a language. So if we can construct a Turing machine that accepts a word written in a certain formal language, then we know that this language is at least semi-decidable. And if the Turing machine also always reaches the rejecting state, when the word is not in this language, then we can say that this language is decidable, a decidable language. Simply because you call a Turing machine that accepts a certain language. So it accepts words that are written in a certain language, a Turing decider. And this, uh, it simply is, it can be explained, of course, scientifically, but let me just tell you, it is simply the case that languages which are accepted by Turing deciders are called semi-decidable languages. And if it is possible to write a Turing machine that accepts words written in this language and rejects words that are not written in this language, then we actually have a decidable language. So this is something which probably many researchers dealt with in times when there were no powerful computers yet, and so you only had the possibility to do theoretical work. And actually, I was quite interested in this theoretical work during my days as a student. So I already knew how to program as an 8-year-old, and I wrote programming tutorials myself when I was 12. So I didn't learn much about programming at university anymore, but I learned a lot about theoretical computer science. So maybe this is not really relevant to, well, the software industry or to what modern computer science is all about. But it's not that uninteresting. It's a hobby for people who are like me, who are into mathematics and logical reasoning and all of this. Well, that's it for this lecture. Bye.